Welcome back. This is a follow-up to the first video on what is the verification scale division. I'd like to pick up kind of where that left off and add a few additional thoughts. So let's begin with lost in translation. I suggest that there are a number of things that are confusing in Handbook 44 because of things that never made it through from R76. In some cases, they didn't make it at all. They never got included in Handbook 44. Perfect example is the elimination of digital rounding error in applying the tolerance. But there are also things that were misunderstood in Handbook 44. The meaning in R76 and the meaning in Handbook 44 are different. So, for example, E was misunderstood as part of the instrument display. But this is never implied in R76. It's not even implied in Handbook 44. So I begin by looking at the mandatory markings for classification. R76 we see marks the class, the maximum and minimum capacity, and the verification scale division E are all mandatory markings. There's an auxiliary marking of D if D is different than E. When it gets translated into Handbook 44, notice what changes. The class and the capacity, same as max, they come through okay. But there is no minimum load marking requirement in Handbook 44. It's handled as a user requirement, and we'll go look at that in a minute. The other big change is that Handbook 44 decided to make D the primary marking for classification purposes. And they mark E if it is different from the mandatory D. And my question is, can we simply flip D and E without some consequences? Well, I suggest that E and D are very different things, and that's what I tried to show in the first video. E relates to classification and accuracy, and it's theory. Tolerances are expressed in the order of magnitude of E, and we were taught to think about the absolute accuracy of 1, 2, or 3E. But in R76, E is used with N to express relative accuracy. That is, if you have more N, you have more accuracy. So as we look at the classes, you can see as we go down the classes, they increase in accuracy by factors of 10. But within each class, what you see is you see an increase in accuracy with more N. But we think of it in steps, but we really shouldn't think of it in steps. Let's look at Class 2. If we look at a Class 2 instrument between 5,000 and 10,000 divisions, the theoretical error of the instrument cannot exceed 0.02%. But as now we get from 10,000 to 20,000, you can see that the percent error, theoretical percent error, drops down to 0.01%, and it hangs at 0.01 from 20,000 to 30,000. Think of it as 2 divisions in 20,000 is the same error as 3 divisions in 30,000. From 30,000 to 100,000, that error tapers down again to a 0.003% error at 100,000. But what's important is these really speak to the whole instrument. It's not 3 instruments at 100,000. In other words, 0 to 10,000 is one instrument, 10,000 to 30,000 is a second instrument, and 30,000 to 100,000 is a third instrument. No, it's one instrument, and essentially the manufacturer is trying to make sure that the D of their instrument is accurate within the percent accuracy you see in this table based on the N for the instrument. D, on the other hand, relates to function or practice, and that's the basic function of the instrument, the least significant digit, that they divide the load by this least significant digit, and it's the only one that's rounded. Now this resolution D is not always the same order of magnitude as E. So sometimes it's equal, what we might call normal resolution. Sometimes D is smaller than E, which we would call high resolution, and sometimes it's larger than E, low resolution. But whether the resolution is high or low or normal doesn't alter the relative accuracy. The resolution of D is independent of the accuracy in E. Independent. That's the whole point of the first video. And error is always the difference between the instrument scale in D units and the true value or verification scale in E units. So coming back to our question, can we flip them? I think there are major complications for Table 6 dealing with verification and Table 8 dealing with use of the instrument. If we look at Table 6 in Handbook 44, what should jump out at us immediately is that all values in this table are in scale divisions. Scale division by definition is D. You can see tolerances in scale divisions, D, and look at the Class 3L. Add 1 D for each additional 500 D or fraction thereof. And so test loads are also expressed in D. But this is not how we actually use the table. When E is equal to D on our instrument, we think D, but we're actually still calculating tolerances in E. And whenever we get an instrument where E does not equal D, we switch over and we read this table in E, even though the table very clearly shows D. Now, if we go back to the source, the R76 table of MPEs, maximum permissible errors, a couple of things I want to do for orientation purposes is first notice that this table is transposed from the table in Handbook 44. In other words, the columns and rows are switched. The second is the R76 tolerances are acceptance tolerances. And finally, and this is subtle, but it's important, the loads in the R76 table are in M for Michael, not N as Norman. In R76, M is defined as the applied load divided by E. And we've been taught to use N, the same N that we use for classification purposes. But you see, R76 reserved N exclusively for classification because N is specifically defined as mark capacity divided by E. But the real critical thing about this table is it's all in E. And notice that this is what we are actually enforcing in practice in the US, even though our table says tolerances are based on D. Now I want to move to minimum load, but I need to do that by going through Table 3, which is the parameters for accuracy class. And what I want to focus on is the column header in column 2. Now this says the value of the verification scale division and in parentheses D or E. Well, which one is it? I think we all know that the verification scale division is E, so the question is, what is D doing here? And if we understand what the table is doing, you're trying to set limits, minimum and maximum, for N, the number of scale divisions, which is capacity divided by E. So why would you have D here? The other thing is, notice in column 2, within a class where the scale divisions E, the verification scale divisions E, get very small, the minimum number of scale divisions changes. So once we get from 100 milligram or greater, you have to have 5,000. But if your E is smaller than that, you only need 100 minimum scale divisions. And as we'll see, this carries over into Table 8. So here's Table 8, and you can see, again, in Class 2, from essentially 1 milligram to 50 milligrams, it also has a different minimum load. 20 D or E, not 50 as we would normally have for Class 2. But the thing I want to focus on is look at the headers of column 2 and column 3. First of all, the column 2 header should be the same as Table 3, but it's now changed to the value of the scale division, D or E. Well, okay, the scale division's D. What is E doing here? It's confusing. And if you look at the footnote 1, it doesn't give you any guidance of whether you're supposed to use D or E. It simply tells you what E is. Also notice in column 3, we're talking about minimum load. And the minimum load is D or E. Well, wait a minute. Can it be both? Think about it. If you have D or E in column 2 and D or E in column 3, there are actually 4 ways to read the table. I can read it with D in both columns, E in both columns, or D in column 2, E in column 3, and E in column 2, or D in column 3. 4 different ways, and who gets to make that choice? Well, ladies and gentlemen, under law, if the law says you shall do A or B, the choice belongs to the regulated party. The regulator has to accept either one. And so I asked the question, what is this minimum load all about? Minimum load is about rounding error. And we basically round to D, the smallest increment of the instrument, and it's always to a half a D. So if we take a load of 2.5 D on our instrument, we have to either call it 2D or 3D. And therefore we make a half a division error in 2.5 divisions of load, which is a 20% relative error. What the codes try to do is limit that. So for class 2, we would limit that to 50D. So half a D in 50D, or half a D in 50E, because E equals D on the red line, our target is 1% relative error. But notice what happens if we keep E at 0.1 gram, but move to D equals 0.01 gram, we reach the same 1% relative error at 5E, 10 times better. And you can see that the blue line remains 10 times better. So now I bring in back to the source, the R76. And now it should become clear why I talked about table 3. Because in R76, minimum load is part of the classification parameters of an instrument. But it's important to see that if I cover up column 5, you should immediately see table 3 from Handbook 44. And if I cover up columns 3 and 4, you should immediately recognize table 8. But what's really important is, as I pointed out before, column 2 has to be verification scale interval E, which it is in R76. But now, when we go over and look at column 5, we see that minimum load is in E. But I just spent 2 minutes explaining that minimum load is a function of D. So what's going on? Well, to understand what R76 is doing, you have to look at the exceptions. The first one appears below the table. It says the minimum capacity is reduced to 5E for a grading instrument, what we would know as a weight classifier in Handbook 44. We're still in E, still kind of counterintuitive. But the second exemption exists in section 3.4 of R76, way away from table 3. It says the minimum capacity is determined by table 3. However, the last column of table 3, we change the E to D for these instruments. Now, the best way to understand this is through examples. So let's go through a series of examples. First example, class 2, 2000 by 0.1 gram, standard E equals D, normal resolution instrument. R76 says the minimum load is 50E, 5 gram. Handbook 44, well, there's the confusion over D or E, but I'm going to show in bold that under Handbook 44, we would normally interpret this as 50D or 5 gram. Next example, the weight classifier. So let's take a class 3 2000 by 1 gram E, 10 gram D weight classifier. In this case, D is equal to 10E. The R76 minimum is 5 gram, but Handbook 44 is kind of a special case because they have this 2 asterisk note that says you use 10D for weight classifiers. So that would be 100 gram, nowhere near what R76 gave. The third example is Class 2, 2000 by 0.1 gram E or 0.01 gram D. So this is the high resolution E equals 10D. R76 would say you switch to D for this instrument, so it's 0.5 gram minimum load. But in Handbook 44, our typical interpretation would be you switch to E, so it would be 50E or 5 gram. But there is a fourth case. R76 addresses a fourth case that got lost in translation in Handbook 44, and that is the ungraduated instrument. So here we have Class 2, 2000 by 0.1 gram E, ungraduated. Now notice it's 0.1 gram E because there are no Ds. It's ungraduated. R76 handles this in the body of the table, 50E for Class 2, with this size scale, verification scale division, 5 gram minimum load. Well, what are we going to do with Handbook 44? How would you interpret it? Well, your guess is as good as mine. I think the table is very nebulous and unclear. Maybe you might get it right and assume it's 50E or 5 grams. But the point I want to point out in looking at this table is look at the first 3 rows here. The R76 expresses the minimum load in E in 3 out of the 4 cases, and it fits in with the table, which is in E to begin with. But if we wanted to fix Handbook 44 and make it more intuitive, that is, base the minimum load in D, we can do it by simply reorganizing the table a little bit. So if we take Class 2, 2000 by 0.1 gram where E equals D, the R76 is 50E or 5 gram, we could say use the body of the table and put the body of Handbook 44 table in D, so the minimum would be 50D in the body of the table. We would have to also include the Class 2 high resolution, E equals 0.1 gram, D equals 0.01 gram, so E equals 10D, the R76 is 50D, and the Handbook 44 would now become 50D in the body of the table. Then you would need 2 exemptions. Just as R76 needed 2 exemptions, 2 were in the body of the table and 2 are exemptions. Okay, we put the high resolution and the normal resolution in the body of the table in Handbook 44. Now what we'll do is we'll put the ungraduated instrument as an exemption. And this one we will say switch the table to E for these devices. And then for the weight classifier where D equals 10E, the R76 is 5E, and we should change Handbook 44 to 5E. Now if you really think 10 is a better number, but it still has to be E. 2 little important notes. Note 1, because there are no Ds, there's a problem with Handbook 44 because D is a mandatory marking in Handbook 44. There's no exceptions. Every instrument must mark D, but there are no Ds. So table S63B, with all the notes about the marking requirements, really needs 2 changes. Note 3 has to exempt a ungraduated instrument from marking of D, and in Note 4, you have to include the ungraduated instrument as a mandatory marking of E. The second note is that column 2, the instrument parameters, column 2 in Table 8 has to be in E. I included this additional slide on Lost in Translation to sort of cover all of the things that I could make up in a short list. The left-hand side are the things that never made it into Handbook 44, and the right-hand side are things that got mistranslated or confused in Handbook 44. As you approach this broad group of issues that I've raised in my proposal, essentially this is where you have to start. You have to understand these translation problems and how they impact all of the code. Several things got lost in translation moving from R76 to Handbook 44, and these are leading to confusion today as we look at using these instruments in the cannabis trade and the jewelry trade. I want to thank you again for listening.